This is the problem we were working on in today's class. You see that we start off with a position time graph, a velocity time graph in the middle, and we have to create from it the position time graph and the acceleration time graph. And the first two data points are done for us here at 1 second and 2 seconds. The displacement for the first second was 2 meters, and then 4 meters for the second, making a total of 6 meters. The next segment that I'm going to calculate the displacement for is this segment right here, from 2 seconds all the way up to 4.5 seconds. That segment there. And if we want to find the displacement from this section, it's a trapezoid, or it's a rectangle plus a triangle. The important thing is that we go all the way down to the time axis here, not just to this point. So a common error would be to go to this point, this line here, but we have to go all the way down to the time axis. So I'm going to do it as a trapezoid. To find the area of a trapezoid, we take the sum of the two parallel sides. So that is 4 plus 16 makes 20. Divide that by 2, so that makes 10. Multiply by the distance between the two parallel sides, which is 2.5. So that makes 25 meters. And since the area is above the time axis, that would be 25 meters east in this case. So if I now go back up to my position time graph, if I take 6 meters, which where I'm already, and I add 25 meters, I get 31 meters. So I'm going to have a point here at 31 meters and 4.5 seconds. So that would be right here. Now if I go back and take a look at my velocity time graph, I see that the velocity time graph is increasing here. So the velocity is increasing, therefore it's accelerating, so the position time graph must have a slope that's increasing. So when I draw in my position time graph from 2 seconds to 4.5 seconds, it should look like this. Let's try that again. See if I can get it a little bit smoother. It doesn't look like the slope is increasing. I'll try one more time. There we go. So at this point right here, the slope just before and after that point should be the same. So we should not get, it shouldn't start sort of going up like this and then increasing. It should start at a slope equal to the slope just before that point. It should be the same as the slope just after that point. So it should be a continuous curve like shown on my graph. If I go back to my velocity time graph, this area here would then is also above the time axis, so this is still a positive displacement, and this is a triangle here. The area of this is 16 multiplied by 1, which is 16 divided by 2 is 8, so 8 meters more here. So I'm already at 31 meters. Add another 8 meters. 31 makes 39 meters. So after 5.5 seconds, I will be at 39 meters. And now my graph should look like this. And the reason for that is because the slope between 4.5 and 5.5 seconds on the position time graph is decreasing, because the velocity is decreasing between 4.5 and 5.5 seconds. So the slope is decreasing. Now I go to the velocity time graph then goes below the axis, so now my displacement will be negative. Let's come back towards the origin. So if I find the area here, it's 8 times 1 is 8 divided by 2 is 4 meters. So it's 4 meters, but it's 4 meters west. I'm going to just put that in there. 4 meters west is the displacement. So if I'm at 39 meters and then I have a displacement of 4 meters west, in the next half a second I'll be at 35 meters. So that would be here. And I will connect those points together with a line that increases in slope. So it's now getting steeper because the velocity is increasing but in the opposite direction. Back to my velocity time graph, this area here up to 7.5 seconds. The area there is, let's see, it's 8 multiplied by 1.5 is 12 meters, but it's 12 meters west. So 12 meters west, I'm at 35 meters. So another 12 meters is, what's that, 28 meters? No. So if I go to 23 meters here and mark a data point, now I'm at 7.5 seconds. And these two lines should be, or these two data points should be joined by a straight line, like so, because the velocity is constant there. And then in the last half second, going back to my velocity time graph, I have this little area in here. It is another 4 meters. So it's still 4 meters west because it's below the axis. And so I will be at, what was I, 23 meters. So another 4 meters would be 19 meters. And the slope here would have to decrease. Something like that. Okay, so there's your position time graph. Now if we go and take a look at the acceleration time graph, to get from the velocity time graph to the acceleration time graph, I measure the slope. So I'm going to take each line segment and measure the slope. The slope is constant in each of the line segments, so the acceleration is going to be constant in each segment as well. So if I start off with the first section right here, this little section here, the slope of that line, rise over run, 4 divided by 1 is 4. So the acceleration for the first 1 second will be 4 meters per second per second. Let's just think about that for a second. So what we're saying is that each second the velocity changes by 4 meters per second. So the acceleration is 4 meters per second per second. You can see that that works out because in the first second on the velocity time graph, the velocity does increase by 4 meters per second. In the next little segment, from 1 second to 2 seconds, the slope is 0. There is no acceleration because the velocity is constant. So now the acceleration drops to 0. Now if I am really careful with this drawing, what would happen in real life is that the velocity would change, or the acceleration, sorry, would change from 4 meters per second, but that would take a tiny little bit of time. So see, you can see how I've, in my diagram there, I've shown the line as having a slight curve to it. But we can, in this physics course, we can just draw the lines vertically like this. To show that it's changing from 4 meters per second to 0 meters per second, but that would actually in reality take a little bit of time. If I go to the next segment, so we want to be careful here when we're finding this slope of this segment, rise over run. So if I go from 2 seconds to 4.5 seconds to make my sort of rise over run triangle, the rise would be from 4 to 16, so that's 12. So the slope would be 12. And then I would divide that by, let's see, 1, 2, 2.5 seconds. And if I take my calculator, if you want, do 12 divided by 2.5, I get 4.8, so 4.8 meters per second per second. So I'm trying to draw that on there, so 4.8 meters per second, something like this, and that goes all the way to 4.5 seconds. Okay, and then we get to the negative slope. So the entire segment from 4.5 seconds to 6 seconds, so this entire segment here is the same slope. So if I find the slope of this area here, this segment here, using rise over run, the rise is actually a fall, and if I sort of make my triangle go all the way down to the bottom here, the fall would be 16 plus 8, which is 24. So the slope would be negative 24, and then the run would be 1.5. So if I do negative 24 divided by 1.5, I get 16. Sorry, negative 16. So negative 16 meters per second. So even though there's a change in direction right here at 5.5 seconds, the slope is still the same all the way in between there. So it actually means two different things, but same value of the acceleration. So it goes down to negative 16 for another 1.5 seconds, like so. And then that's it. So that's the end of the graph. Let's take a look at all three graphs now, and we'll have a look at some relationships. So first of all, we see that on a position time graph, if we start off with curves on the position time graph, they become straight lines on the velocity time graph. A straight line on the velocity time graph, such as this little section right here on the position time graph, I should say, becomes a flat line on the velocity time graph. And sloping lines on the velocity time graph become horizontal lines on the acceleration time graph. So the graphs sort of get simpler and simpler as you go from position to velocity to acceleration. If we want to go this way with our graphs, then what we would do to go this way is we would find the slope. So the slope of the graph will take us to the next graph down. So if I take slope, if I take the slope, then I can go this way, and if I want to go the other way, so from the bottom towards the top, then I find the area. And remember that when you're finding the area, you always find the area between the graph and the time axis. So that's what you're doing for area. So if you can check your solutions against what I have here, that would be great, and then we'll go from there. We have lots more practice questions available to you if you need them. In this technique, this is about the most difficult technique from graphing, is creating one graph from another. Simpler techniques or problems that you could be asked to solve would be just to find the displacement or velocity of something from one graph.